Okay, here you can see a digital logic simulator that will showcase the functionality of our circuit. There's different cases. The first case is an eastbound train striking the west switch first. That's this switch here. The train is long enough to contact all three switches at the same time. The second case would be the case where the westbound train striking the east switch first. The train is long enough to contact all three switches at the same time. The third case is if the train is very short and only hits one switch at a time from the west side. The fourth case is if the train is very short and only hits one switch at a time from the east side. So we have our switch inputs. We have them inverted. For some cases we need that. We have an OR gate here, a couple AND gates, various input sizes, another OR gate, 3 JK flip-flops. The Q's of these are outputs. So the output of Q2 for JK flip-flop is our signifier if the train is westbound or not. If it's on, it means it's westbound. If it's off, it's eastbound. Our JK flip-flop Q2 indicates there's a train on the tracks. Our JK flip-flop Q0, when that's on, it means there's a train in the crossing. Or if the first output is on, the second one's off, the third one is off, then we're waiting for the final switch to clear from either side. After the final switch clears, the machine resets and goes back to the start state. So going for the first case, we have an eastbound train. It strikes the west switch first, so that's struck first. Now we have an indication that there's a train on the tracks. The train hits the next switch, the middle of the crossing. This LED goes high. That means that there is a train in the middle of the crossing. So if the train strikes the next switch, it stays the same. But now the rear car clears the first switch that it struck. And then the rear car clears the middle of the crossing. This should make our output go to 0, except for this output here. As you can see, now we're just waiting for the train to clear the final switch, the east side. And now we're reset and ready to go from either direction again. So the second case is a westbound train striking the east switch first, so we strike the east switch. Now we have a westbound train, an indication that the train is on the tracks. And then we strike the middle switch. That means there's a train in the crossing. Then we strike the final switch. And now the train clears the first switch. And then the train clears the middle switch. So there's no more train in the crossing, no more train on the tracks. So we're waiting for the train to clear the final switch and reset and go back to the beginning. So it's reset and it's waiting on another train from either direction. So our third case is if the train is very short and only hits one switch at a time from the west side. So it hits the west switch. It's very short, so it only hits one switch at a time. So we have a train on the tracks here, and we turn it off, and then we hit the next switch. Now we know there's a train in the crossing, and then we hit that switch off, and then we turn on the last switch. The train hits the last switch. That means we're waiting for a reset. As soon as that clears, it resets and goes back to the start state.
Okay, here you can see our logic circuit prototyped out on a breadboard. The first thing we have here is our 12 volt battery. This is our 12 volt supply. This will supply the signals from the tracks. We have a 5 volt power supply. That's to run our logic ICs. Over here we have 3 switches, a west switch, a middle switch, and an east switch. These would all emulate the track switches. Next to that we have 3 NPNs with resistors and LEDs. These are set up in an emitter follower configuration. They take the 12 volt input signal and output 5 volts for use with our logic ICs. Over here we have our output LEDs, Q2, Q1, and Q0. These are outputs from our JK flip-flops, which are over here. Up at the top here we have our clock circuit. It's a 555 timer. This clock circuit triggers the JK flip-flops. Over here we have a hex inverter. We have a 2 input AND gate, a 2 input OR gate, 4 input AND gate, 3 input AND gate, another 4 input AND gate, and obviously the JK flip-flops. So the first case for our circuit is when a train is eastbound. It hits the west switch first. So we hit the west switch first. You'll see that our Q1 input or output went high. That indicates that there's a train on the tracks. Then after hitting S1, the train would hit S2. You see Q0 goes high. That indicates that there's a train in the crossing. After that, the train would hit S3. You see nothing happens. It stays the same state. And then the train's rear car would leave the first switch. Same thing, we're in the same state. Now the train's rear car would leave the middle switch, or the crossing. So our train on the tracks has gone low. Our train in the middle of the tracks has gone low. And now we have a 1 LED Q2 on that's just in a wait state, waiting for the train to clear the third and final switch, which would reset the state machine. So now that the state machine is reset, we can take a train from either direction again. So we'll do it from the reverse direction this time. This is the east switch, so the train is going west. So the train hits S3 first. This status indicator right now means that the train is westbound. This one, Q1 again, means that there's a train on the tracks. So then after hitting S3, the train would hit S2. So now Q0 lights up. That lets us know that there is a train in the crossing. So after it hits switch 2, it'll hit switch 1. We're in the same state. The final train car will clear switch 3. Same state. The rear car will pass switch 2. That means it left the crossing. So now our output, these two outputs are 0. They're low. And then the rear car will it'll clear switch 1, and the state machine will reset, and we'll be ready again for a train from either direction.
Okay, here you can see the design we use for our voltage regulator. This is meant to power our logic circuit. So for this circuit, we have a few design constraints. We want the maximum output voltage to be less than 5.25 volts, the minimum output voltage to be 4.75 volts or more. We want this circuit to take in a higher supply voltage and buck that down to a lower output voltage. We want this range to be, let's say, 9 volts to about 14 volts. This will be useful for us because our system would be powered by a 12-volt lead acid battery. Now, the output voltage of a lead acid battery can vary from, let's say, 11 volts for a discharge battery up to 13 volts or so for a fully charged battery. Another design constraint for this regulator, we want to have load variation. So we want to be able to put different loads on the supply and still have the same output voltage. So you can see here, this is our output voltage. It looks a little messy, but it is right around 5 volts. It's only up or down a little bit, so it has very, very little ripple. So the basic function of this circuit is there's a 555 timer in astable multivibrator configuration, to comparing op amps, a 5.1 reference Zener diode. So these op amps, they compare the reference to the output voltage and then modulate the switching signal or the for the buck converter, which is right here. And it keeps the output voltage down to around 5 volts.